Hi everyone, I'd like to work through one more example of using a polynomial to represent some real world situation and then answering questions based on the equation for that polynomial. This last one is a little different because we do have to find the equation ourselves. So let's walk through that and then we'll work on answering the question. Okay, so we're cutting out what's supposed to look like a pizza box. So we have a hinged lid here. So we cut out squares from each corner, which we've definitely done before. But we also cut out the square in the middle, and then we fold up all these little green tabs, and then we close it on itself, and it hinges here and here, and you have a box with a lid. We want to find a formula for the volume of the box as a function of the size of the cutout. So this is my x. The cutouts are all squares, so both dimensions are x. And we're supposed to identify a reasonable domain for that thing. And then we're supposed to try and estimate the value of x that will give us the biggest volume. Okay, so to start this off, I'm looking for the volume. You don't think I'm repeating things here. I see x defined, but I don't see my volume variable defined. So I'm going to call it v, and v is the volume of the box. So make sure you declare any variables if they're not given to you. First, the general idea is, how do you find the volume of the box? And this is something you guys should know. I don't expect you to know all sorts of volumes, but this one I want you to know. So, what am I doing? I'm going in a weird order and it bugs me. You can go in whatever you want, order you want, but I'm going to go length times width times height. That's how I say it to myself in my head, so that's how I will write it. Okay, so the length and the width part, let's see, corners, middles, got it. Okay, so the length and the width part are kind of up to you. I'm going to say that, it doesn't matter, let's say this way is the length. So again, this flap right here is going to fold up and stick out, so we'll call that length. And we'll call this width. And then the height is actually, if you're looking at this right, the easiest to find. The height is determined by this length right here. So the height is actually just an x. So when we go for volume as a function of x, we're going to get a length, we're going to get a width, and then the height is just a plain old x. Okay, I think I'm going to go for the width first because that's similar to something we've had to do before. If the width of the cardboard is 20 inches and we cut out x inches from each side, the width of the box will be 20 minus the 2x that we cut out. What's a little trickier is the length. So basically here, if we call the length L temporarily, I'm going to do just a little bit of scratch work. Let me see where I want to put it. The 40 inches that we have across the length of the cardboard actually adds up to be, or is added up to, I don't know how to say this. To get that, we would need to add up 2 lengths and 3 x's. So it's 2 L's plus 3 x's. And we're interested in the L, so we can solve. If you can do this in your head, great, but it's a little messy. I think it's worth trying to write a little workout. So 40 minus 3x over 2 equals L. Okay, I'm debating. I think I'll just leave it that way. You could definitely rewrite it, but I don't think we really need to do any work with it after this. So you could make it, just if you're curious what I was tempted to do, a 20 minus 3 halves x. You could split the top of that fraction, but we'll just leave it be. Okay, so there's my formula, and that hopefully is the hard part. From there, we want to go looking for the x that will give us the largest volume. So again, a graphing calculator is going to make this a little bit easier for you. If you don't have a graphing calculator, try and get a rough sketch of this thing so that you can figure out where you expect your maximum to be. So this has zeros at 0. And at 10, and what does this one give me? 40 over 3, 13 and a third, I think so, 40 over 3, yeah, okay, so 10, and then just after that, 13 and a third, those are my zeros. If I multiply it out, I would have a negative 3 halves x, a negative 2x, so that's going to become a positive 3x squared times x, positive 3x cubed. So our global behavior is going to be right side up cubic, which means I'm going to come through here. Those are all multiplicity 1, first powers, so they're all cross throughs. Okay, so this is the whole thing. I don't think all of this makes sense, but that's what the polynomial looks like. I definitely don't think we should be looking at negative x's, so let's get rid of that. Deciding where to cut it off on the other end, this is going to help us answer our reasonable domain question. So the smallest x could possibly be a 0. It's a terrible choice. It doesn't actually give us a box. We don't have any cutouts, but it does have some meaning. We just have our piece of cardboard. The biggest that x can be is actually the 10. What happens here is x gets bigger and bigger and bigger, and when x equals 10, you run out of anything to cut from this shorter side. So we've completely run out of cardboard. We won't have anything to fold up here. So we actually don't want to see any of this either. So we're only interested in the part of the graph between 0 and 10. If you are trying to guess and check your way to this, if you don't have a graphing calculator to do this on, remember that this will be pushed to the outside a little bit. So I would start looking between 0 and 5. So maybe plug in a 2.0, a 2.5, and a 5 and decide which two of those it's between. And then you can narrow it down a little more than that. Let's see. If you do have a graphing calculator, you can plug this whole mess in. We're going to need some extra parentheses. 40 minus 3x over 2 times 20 minus 2x times an x. And I've already decided that the part that makes sense is the 0 to 10 part. So I'm going to choose that, and then I'm going to go get my zoom fit 0. And that will pick my y values for me. So if you're using zoom fit, make sure you choose x values. Okay, there it is. And again, I would expect that peak to be before 5. So there's 5, 625. I hate when this is in the way, so I'm actually going to go in there and just move this up a little bit. I'm going to make it 750. So my y max, it had it 673 or something like that, which is probably close to exactly where the max is, but just so that I can see what's going on, move it up a tiny bit. Okay, so there's my 5, 625, and it looks like it's a little before that. Okay, so I'm watching this y value 665, 668, 671, 672, 673, 2937. Okay, so I think that's the biggest one I get. 673.76, so that's approximate. It's not perfect. Again, if you want to remember the button strokes to get your calculator to do it a little more perfectly, you hit second trace to bring up your calculate menu. We're looking for a maximum. So you can arrow left or right, or you could just say, well, it's definitely bigger than 0. You can type in the left bound 0 and hit enter. It's definitely smaller than 10. We're talking about the x values. You could type in 10 and hit enter. And then guess shouldn't matter. And there it is. Okay, so this is at 3.77, 637.84. Okay, so the last thing we'll want to do here is just reread the question, make sure we're giving the right answer. Find the values of x that result in the box with the largest volume. Okay, so this is v and x. So this is the volume. The biggest box we can make has a volume of 637.84 cubic inches. The question wasn't asking that. It was asking what x we should choose. So approximately 3.77 inches would be the answer. All right, thanks for watching.